Hey guys, Assalamualaikum. In this video, we will do a little bit of review on all of the hypothesis testing that we've learned throughout the semester. The first test that we have learned is called the one-sample mean test. Now in this test, we use it when we want to compare the population mean against a hypothetical figure. Okay, so how do we write the hypothesis? The null hypothesis is that we assume that mu is equivalent to a hypothetical figure. It could be anything. So let's say I choose 5. Okay, so the alternate is the population mean is not equals to 5. Okay, and as usual, the sign for the alternate hypothesis can also be greater than or lesser than depending on the question. So what's next is to calculate the test statistic, right? Now, in calculating the test statistic, it depends on two circumstances. One is if we have a large sample size, okay, and usually we know the population standard deviation. Okay, so in this case, the test statistic that we use is the Z distribution. Okay, so to get Z, this is the formula: x bar minus mu over sigma over square root of n. Okay, because we know sigma, that's why we put sigma here. But if we have a large sample size but we don't know sigma, all we have to do is still we use the same formula, but instead of using sigma, we just substitute it with S, which is the sample standard deviation. Okay, very simple. Now the next situation is if we have a small sample size. Okay, usually when we have a small sample size, we don't know what sigma is. Okay, so this is the second situation. Now, when this happens, we cannot use the Z. So what can we use? We use the T distribution. And the formula is x bar minus mu over S, because sigma is unknown, so we substitute with S, over square root of n. Now, don't forget, when we use the T distribution, we must also know the degrees of freedom. In this case, the degrees of freedom is n, or sample size, minus 1. Why? Because we're dealing with one sample. Okay, the next test that we have learned is the two-sample mean test. Two-sample mean test. Now for two samples, it depends on whether the samples are independent of each other or dependent on one another. Okay, so now let's focus on the independent two-sample mean test first. Let's put here independent. Okay, what that means is both samples have nothing to do with each other. They have no relationship. All right. So for the case of an independent two-sample mean test, it's further divided into two types of tests. Okay, the first case is when we have a large sample size, and in this case, usually the population standard deviation is known. Okay, so how do we write the hypothesis first? Now remember, the objective of a two-sample mean test is we want to compare between two population means. Okay, that is why the null hypothesis is written this way. Mu1 is equals to mu2. What it means is here we assume that both population means are equal to each other, and then alternatively we assume that, or alternatively we say that they are not equals to each other. And of course, the sign here can also be greater than or lesser than depending on the question. Okay, so this is the first thing that you should know how to write the hypothesis. Now, the second thing that's important is, of course, how to calculate the test statistic. Okay, test statistic. Now, in this case, because we have a large sample size, okay, and the population is known, we will use the Z distribution. Okay, so let me zoom in. Okay, so the Z here, okay, remember, because now we've got two samples, right? If we have two samples, that means we have two sample means. Therefore, we find the differences between the two sample means, okay, now over this combined standard error. So the standard here would be the variance for the first sample over the sample size for the first sample, plus the variance of the second sample over the second sample size, and square root it because it's standard error. Now, why do we use sigma here? It's because, see the assumption? The assumption is the sigma is known. Okay, that is why we can use the sigma, or population standard deviation. Okay, so this is the first case. Maybe I should put it here. This is the first case. Now, the second case is if you have a small sample size. Okay, that means n is less than 30. And usually when we have a small sample size, the population standard deviation is unknown. So in this case, we use what's called the pooled t-test, right? So let's put it down here somewhere. We use the pooled t-test. Okay, so how do we write the hypothesis for pooled t-test? It's the same way, okay? Because regardless whether it's a small sample size or large sample size, the objective of the test is the same. We want to compare two population means, okay? So even for a pooled t-test, this is how we write the hypothesis. So the difference lies in how to calculate the test statistic, okay? So how do we calculate the test statistic? Because it's a pooled t-test, so therefore our test statistic is the t-distribution. Okay, so recall, before we can use the t-distribution, we need to find something that's called the estimate of the pooled variance first. Okay, so we need to find this first. So here is where we find the first degrees of freedom, first sample size minus 1, multiply with the sample variance for the first sample, plus the second degrees of freedom times the second variance, over the combined degrees of freedom, n1 plus n2 minus 2. Why minus 2? Because now we've got two samples. Okay, once we find this estimate of the pooled variance, now we can find the t, okay, which is our test statistic. Okay, now the top part, or the numerator, is exactly the same as the top part for the test statistic using z, okay, because up here is we're basically finding the difference between the two sample means. Okay, so up here is the same. The difference is, of course, at the denominator or the standard error. So in this case, we will use this estimate of the pooled variance that we have just now, that we've calculated just now, over 1 over the first sample size plus 1 over the second sample size, and because it's standard error, we squared it. And don't forget, as always, whenever we use the t-distribution, we need to know the degrees of freedom. Okay, so in this case, the degrees of freedom, let's write it down here, the degrees of freedom is n1 plus n2 minus 2. Besides independent samples, sometimes the two samples are dependent on one another. Okay, so in that case, we've learned another test called the dependent sample test. Now, to conduct this test, we need to create a new variable, the d. d here is basically the distribution of the differences between the two observations. Okay, so now once we have the list of the differences, we need to find the d bar. Okay, remember, d bar is basically the average of all of the differences. So a sum of all of the differences over n. Okay, and then besides the d bar, we also need to find the standard deviation of the differences. Okay, so here in this case, each and every value of the difference minus the average here, then square it, now we sum it. Okay, again up here is the sum of squares over n minus 1. Okay, and because it's standard deviation, we square root it. All right, so we've already found this. Now once we have these two, okay, so we basically want to calculate the test statistic. Right, now the test statistic is of course different. In this case, we use the d, but for the dependent sample test, we use the t-distribution. Okay, but the way to calculate the t is not the same as the pooled t-test. Here, we have to use the new distribution of the d. So up here would be d bar over the standard deviation of the differences over the square root of n. Okay, now you may have noticed that I've forgotten to write down the hypothesis. Okay, please write down the hypothesis first. Okay, so to write the hypothesis for a dependent sample test is mu d equals to 0. What this means is we assume that there is no difference between the two observations, okay, universally. And the alternate is there is a difference. Okay, now as always, the sign for the alternate hypothesis can either be positive or greater than, or negative, lesser than, depending on the question. And don't forget, since we're using the t-distribution, we must also write down or know the degrees of freedom. Okay, in this case, our degrees of freedom is n minus 1. Now, although this is a dependent sample test, okay, but it's minus 1 because they have a relationship to another. So although we have two observations, but they're essentially coming from the same source. Okay, and then the next test that we've learned is called the equality of variance test. Okay, so if you've noticed, so far all of our tests was on means, right? averages. So this time is the first time we're going to test variances. So how do we write the hypothesis? Okay, it's not mu this time, but population variance. So here we're assuming, okay, the hypothesis is that two population variances are equals to each other, as compared to they are not equals to one another. Okay, and as always, the sign of the alternate hypothesis can also be greater than or lesser than, depending on the question. Okay, now to calculate the test statistic, okay, we will use a new distribution. For the equality of variance test, we don't use the Z or the T distribution. Rather, we use the F distribution. Okay, so how can we find the F test statistic? We just find the ratio between the two sample variances. Okay, what that means is we take the larger variance, we divide it with the smaller variance. Okay, so make sure the one up here, the numerator, is the larger variance. Okay, and for the F distribution, it's similar to the T, whereby you need to calculate the degrees of freedom. So for the F distribution, when you are doing the equality of variance test, the degrees of freedom is basically n minus 1. But we have to find the degrees of freedom for both the numerator and the denominator. The next test that we have learned that we also use the F distribution is ANOVA. Okay, so remember, ANOVA, the objective of the test is when we want to compare several population means. Several meaning more than two. Okay, because if we're just testing two, we can just use the pool T test or the independent sample test. Okay, so here, how do we write the hypothesis? Let's assume we have three, okay, samples coming from three populations. So mu1 equals to mu2 equals to mu3. Remember, the null hypothesis is always we assume they're all equals to each other. Alternatively, at least one of them are not the same, right? So at least one of the population means are or is different from each other. Sometimes you can say that not all of the population means are equals to one another, so similar. Okay. So if you remember, the way to calculate the test statistic for ANOVA is extremely long, right? You actually have to have the ANOVA table. Okay, so remember, before you can come up with the ANOVA table, you need to do some calculations. You need to find the grand mean, then you need to find the column mean, then you need to find the SS total, sum of squares total, and the SSE, or sum of squares for the error. Then you minus them together, you can get the SST. Okay, once you've done all of those background work, now you can come up with the ANOVA table. Okay, recall the table. Okay, it starts with the sources of variances, right? The source of variance. Or what causes the variance? Is it due to treatment or due to error? Okay, remember, treatment here is basically the differences between groups, whereas error here is the difference within the group. Sometimes here is also called the explained variances. Okay, and down here is called the unexplained variances. Okay, and of course you have the total variance. All right, now the next column would be our sum of squares. Okay, should be a long one. Sum of squares. Here would be the SST due to treatment. Here's the SSE. If you add them together, you have the SS total. All right, then here would be the degrees of freedom. Okay, perhaps the easiest degrees of freedom would be the total, which is n minus 1. Okay, for SST is k minus 1, and here SSE is n minus k. Again, to get this, you can add these two to get this one, or if you have one or the other, you just minus one from the other to get the other one. Okay, then the next column would be the mean square. All right, here would be the mean square due to treatment. How we get this is basically SST divided by the degrees of freedom for the treatment, which is k minus 1. Here's MSE, and to get that is basically the SSE here divided by the degrees of freedom. Okay, oops, n minus k, right? So we just concern with these two. There's no total here. Okay, and finally, there, we calculate the F. Remember, this is the objective of why we're doing all this, right? To get the test statistic. The F is basically simply MST over MSE. Okay, and just like before, because it's the F distribution, you have to make sure that the bigger value is at the numerator. okay, because the F distribution is positively skewed, so you want to get a large value. And then we move on to another test, which is the tests for proportions, okay? So if you notice, before all of our tests was on means and variances, so now we're testing proportion this time, okay? So the test for proportion is divided into two cases. One is for a one sample proportion test, and the other one is two samples, okay? Okay, so the objective of the one sample proportion test is we want to compare the population proportion against a hypothetical figure. So the way to write the hypothesis is H null pi this time, okay? I'm sure it's a pi because this is a proportion test. Remember, we always write the population parameter, right, for the hypothesis, equals to a particular proportion, let's say half, okay? And the alternate is pi is not equals to half. And again, the sign here can either be greater than or lesser than, depending on the question. Okay, so now how do we calculate the test statistic? To calculate the test statistic for proportion, we always use the Z distribution, okay, because there's an underlying understanding of the binomial distribution when it comes to proportions. So to find the test statistic for a proportion test, we use P. Okay, remember, pi is the population parameter, so the best estimate for pi is P. So we find the sampling error, P minus pi over, okay, pi times 1 minus pi over n and square root it. So this is basically the standard error. Okay, so this is the test statistic for the test for proportion one sample. Now we look at the two samples proportion test. Very simple. How do we write the hypothesis? This time we've got two samples, right, which comes from two populations. So obviously we want to compare whether the population we want to compare whether the two population proportions are equals to each other or not. So here pi 2 equals to pi 1. Alternatively, they are not equals to each other, or one can be greater than the other, or one can be lesser than the other. Okay, so this is how we write the hypothesis. Can you see the difference? Okay, so how do we calculate the test statistic for a two sample proportion test? Okay, very similar, only this time for the numerator, the top part up here, because we've got two samples, therefore we will have two sample proportions, right? So up here would be P1 minus P2. Divide by, okay, down here, this is where it's a bit different. Okay, since now we've got two samples, we need to calculate something first. Okay, we need to calculate something that's called the pooled proportion, or the combined proportion first, okay, which is x1 plus x2 over n1 plus n2. Once we have this combined proportion or pooled proportion, we will use this as the standard error, okay? So how do we write this? It's very similar to how it is for the one sample. Okay, we take the PC. Instead of pi, we take PC because now we've got two sample proportions, right? So we take PC times 1 minus PC over the first sample, okay, plus PC again times 1 minus PC over the second sample. And since it's a standard error, we square root it. Okay, I probably should have mentioned that when we started the test for proportions, we've actually entered the nonparametric method. Okay, so the nonparametric method is basically, maybe I should write it down. The nonparametric method is basically when we don't have to assume normal distribution for our distribution, okay? So it could be other than normal. So under here, we actually learned the proportion tests, okay, or tests for proportion. And then, of course, the next one is the goodness of fit test. Okay, and the third one is the test of association, or the contingency table analysis. Okay, so these three are the tests under the non-parametric method. Okay, so we can use this, especially in the case of test of association, we can use this when the variables are nominal or ordinal in nature. And basically when we don't have to assume that the distribution is normal, okay? So we've already looked at the test for proportion. Now let's look at the goodness of fit test. So how do we write the hypothesis? Now remember, for a goodness of fit test, there are two cases, okay? One is when we have equal expected frequency, and here is when we have unequal expected frequency. Remember, the objective of the test here is we want to compare whether what it is that we expect, you know, our expectation is equals to the reality or what is observed. Okay, so that is why for your null hypothesis, okay, I know it's very easy to just put FE equals to FO, okay, but it's actually not that straightforward. You can, of course, you can say there is, let's see, there is no difference. Okay, there's no difference between observed frequency and expected frequency. Okay, you can say this. Okay, so down here, the alternate would be there is a difference. Okay, there is a difference between these two. Now, you need to remember that no difference is at the null. Okay, how to remember this? Null. Null, nil, zero, no, no. Okay, so you put the no difference up here. Okay, because many students always put it the other way around. I don't know why. So the alternate is there is a difference between these two. But as you may have seen from our class exercises, when you interpret the goodness of fit test, it can be a slightly, complicated because you really need to understand the context of the question. Okay, but this is basically the general idea. All right. So how do we calculate the test statistic? Remember, the test statistic, okay, we use something different. We do not use the previous distribution. We don't use Z, we don't use T, we don't use F. What we use is this distribution called the chi-square distribution. Okay, so the formula for the chi-square is, okay, we need to find the difference between our observed and expected. Okay, FO minus FE, we square the difference, and then we divide by the expected frequency. And since there'll be a lot of them, all of this, we sum it all up. Okay. Okay, so before you can calculate the test statistic, you need to find the expected frequencies first, okay? So how can we find the expected frequencies? It depends on whether it's an equal FE case or an unequal FE case, right? Okay, so we've done these two. Now finally, let's look at the test of association, or also known as the contingency table analysis. Now, we use this test when we want to see if there's any relationship between two qualitative variables. What that means is if your variables are qualitative and is nominal or ordinal in nature, so we can use this test of association. Okay, so how do we write the hypothesis? Okay, so the null hypothesis is there is no relationship, okay, no relationship between, okay, whatever the two variables are, and the alternate is there is a relationship, okay, between whatever. So as remember just now, since this is null or nil, so the no relationship should be at the null hypothesis. Okay, so how do we find the test statistic? Just like the goodness of fit test, the test statistic here we also use the chi-square, okay, meaning FO minus FE, square it, and then divide by FE, and all of it we sum. Okay, so as you noticed here, the test statistic formula is the same. The difference is how we find the expected value. Here, for the goodness of fit test, okay, for the goodness of fit test, we find the expected value depending on the case, whether it's equals or unequal case, okay? But for the contingency table analysis, how we find the FE is, okay, if you go back to the video, you can see that to find the FE is basically row total multiply with the column total over the grand total. So you do this for one value of FE. Then of course it depends on how many cells there are, and you keep on going until you finish all of the expected values. Oh, and another thing, don't forget that whenever we apply or use the chi-square distribution, we need to know the degrees of freedom. So for the goodness of fit test, okay, for the goodness of fit test, the degrees of freedom is k minus 1, okay, where k is the number of categories. Whereas if we're using the test of association, and we also use the chi-square, right, is here, the degrees of freedom is basically the total row minus 1 times total column minus 1. Okay guys, so basically that's it, all of the hypothesis tests that we have learned. One more time, let's see, we have, this is the first test, test number 1, and here is test number 2, which is the independent sample test, and of course is the test number 3 is the pooled t-test. Okay, test number 4 is the dependent sample test. Test number 5 is the equality of variance test. Test number 6 is ANOVA. Okay, and then test number 7 is test per proportion, which are 2. So here's test number 7, one sample proportion test. Test number 8 is two-sample proportion test. And of course, here we have test number 9, which is the goodness of fit test. And finally, test number 10 is the contingency table analysis or the test of association. Okay, so 10 tests.